Anyways, we can get started. I don't know if I have the share. Um, can you all see my screen? Yeah. Are you seeing it in full screen? Okay. So let's get started. What is that? So I won't be when I go full screen. I'm using Linux. So when I go full screen, I won't be able to see any of your messages on the chat. So I would appreciate if you can unmute yourself and ask a question, or stop if you have any questions or trouble. All right. All right. So this would be a continuation of what Ben just discussed, but instead we won't be looking at individual receivers or uh, doing the individual data analysis for individual receivers, such as the phase leveling or the code, the DCBs or the code analysis. But instead, we have something called a database, which we call Madrigal, that's hosted by MIT, especially the people at MIT Haystack Observatory. Those are the people who are responsible for maintaining and updating that database. And what we would be doing instead is looking at how to fetch data from Madrigal and analyze it so that you can make TEC maps and even time series plots. And in addition, we will also discuss about simulation. I don't know if anyone is actually aware of that, but it's simply some ionospheric processes that can lead to severe disturbances in GNSS signals, and we will look into what those are, and let's try to do some exercise on both of that, right? So I'll start with a brief summary. Let's start with what TEC is or TEC is. It's simply, as Ben mentioned, the line integrated electron density between a satellite and a receiver. So if you have a receiver on ground and a GPS satellite that's roughly 20,000 kilometers above us, then it's simply the number of electrons between the receiver on ground and a GPS satellite at the 20,000 kilometers. You would have contribution to the electron density primarily from the ionosphere, but also you could have some contributions from the plasma sphere, so roughly about 1,000 kilometers. But the main contribution would be coming from altitudes between roughly 90 to 400 kilometers or so. Okay, so it's simply expressed in units of 10 to the power 16 electrons per meter squared, which we call one tech unit. So whenever you hear about the tech unit, remember this is the amount of electrons per meter squared that we are talking about. Right? And we can measure the ionospheric tech using two approaches, one using the pseudo range code and the other one using the carrier phase measurements. And obviously, you need to have two different frequencies because, as you would recall from Ben's lecture, subtracting the measurements from two different frequencies would actually give you an estimate of the tech along with other noises and biases. Now, most of the TECs or the tech that Ben was discussing uh, was the slant tech or the tech that's integrated along the line of sight between a receiver and a satellite. But in scientific practices, or at least scientific literature, when people are interested mostly on comparing the observations between satellites, or like someone asked earlier, if you want to measure or compare the tech measurements between a geomagnetic activity and a geomagnetic quality, then always we would try to convert TEC from slant units to vertical units. And that's mainly to remove this geometrical bias between different satellites that are at different elevations. So if you have a satellite that's right overhead you, as compared to a satellite that's right around the horizon, then the slant tech for a satellite that's close to the horizon would be higher than a satellite that's just above you overhead, just because of the geometry. But if you want to really measure what the corresponding vertical tech is at the two different locations, so that we want to know what the spatial differences between the TEC values, removing the geometrical bias, then we go for the vertical tech. And we usually use it for, like I said, for mostly for scientific objectives where you want to know how the TEC values are varying at two different locations by removing the geometrical bias. And question 2 here gives you how to convert from vertical from the slant tech to vertical tech. It's a simple conversion factor where you have the radius of Earth, the elevation angle or the size, sine of the elevation angle of the satellite, and there's a term h sub I, that's the Ionospheric Pierce point, and that's simply the altitude where you assume the entire ionosphere to be located. So usually the ionosphere is an extended medium, roughly between 90 to 400 kilometers. That's where we assume the entire, or the majority, 90% of the ionospheric density is concentrated. But since it's a big region, we usually, for theoretical considerations and for practice, for data analysis, we assume that the entire ionosphere between 90 to 400 kilometers can be stretched down to a thin shell that can be around 350 kilometers. That's usually the practice that we take. But you're also free to adjust the altitude of this ionospheric shell. And in the figure here, it's this red line that you see where we assume the entire ionosphere to be concentrated. And that's what we call the ionospheric Pierce point, or the point where the GNSS signal meets the ionosphere. That's h sub I. And that's what you have in the denominator here. So you can assume an altitude of 350 kilometers, and this is the altitude for Madrigal, the MIT people assumes for the ionosphere when they make vertical tech data available to the public. But this is also one of the drawbacks on using the already available data, like Ben mentioned. So let's say you are in one of the high latitudes where you have most of the electron density at E region, where aurora is mostly found, so roughly around 120 kilometers. So in those cases, the vertical tech that you calculate would be having a lot of the uncertainty or error because of the uncertainty of the error in the ionospheric Pierce point. So instead of using 350 kilometers, in those cases, you should be using 120 or 150 kilometers. But in those cases, you will have to reanalyze all the data from the receivers, and that's where the approach shown by Ben did. So that's a classic approach, what everybody follows. And that's the back of the envelope approach, even what Madrigal follows, in order to make this vertical tech data available for all of us. So if you want to set up a receiver on your own home or in a university, in your neighbor's home, just for scientific purposes or for fun, then you will have to know how your branch. So in those cases, you will have to do this like pseudocode and carrier phase analysis, estimate errors in the receivers and the satellite clocks, estimate biases, estimate, and then also do this phase level between the carrier phase measurements and the pole measurements. But everything what Ben showed has been done and it's readily available for you in the Madrigal database, and that's what we would be using at least for this session. So I would be giving you an hands-on approach on how to download data from Madrigal and plot them, so that you don't really have to worry about estimating biases or the corrections because of the sampling and the receiver errors. Everything has been corrected for within Madrigal by the scientists at MIT stack. But just remember that it's not free from errors. There are still errors in Madrigal data. It's like sometimes up to 5 to 10 decades. But if you're not interested in the absolute TEC value, but you want to really know like how the TEC structures are moving, or if you want to know like during a storm, what is happening in the ionosphere, how was the ionospheric dynamics behaving during that particular period, instead of worrying about the exact TEC value, then this is a very, very, very good database to have. So we will be using two types of vertical TEC data. The first one has a temporal resolution of 5 minutes, and that's usually graded in a 1x1 geographical latitude longitude. So what Madrigal does is, so Madrigal is simply a database that hosts data from the upper atmosphere instruments, a lot of upper atmosphere instruments. So not just GNSS receivers, so they also have data from in-orbit scatter radars like iScan system in Europe, the Millstone radar, and the Poker Flat in the US. Then a lot of Fabry barrel interferometers, data from in situ measured in situ satellites such as TMSP or the Polar Orbiting Environment satellites, and many more like magnetometers. I'll show you. Like we'll go to the website, and I will actually show you how to download this data. But before that, this is how, or these are the two types of data that we look at. So vertical TEC data with a temporal resolution of 5 minutes, and the typical file name would be labeled by this particular TEC being 1 degree by 1 degree by 5 minutes. So that's the file name that you should be looking for. But there is also a higher resolution data available at Madrigal, and that's a resolution of 30. So that's much more precise. So if you want to really look at what's happening at the lower time scales, then you should be looking at this higher resolution data. The only difference is that the binned data, or the higher, the 5 minute resolution data, is usually about like 150 megabytes, but this 30-second data is very, very big. It's huge. It's about 12 to 15 gigabytes. So that's why I had let Amadi know, or sent you a slide, a type of slides actually, a PDF slide containing some information how to download this data, so that it takes some time for you to download it into your own computer. So if you have done that, that's good. If not, then just follow up. I'll be showing how to download the data, but it would be taking a lot of time depending on your internet speed. Right? So we'll be going into Madrigal, and we'll be, so this is the website. I will be posting it in the chat so you can follow up with me. If you are a new user, if you have never used Madrigal, then you might need to give some login credentials. You don't have to give a password, just your, I think, yeah, you need to give your user ID and an affiliation, and an email ID possibly. That's it. So, but anyone having any question before we go into the database and start pulling up data from Madrigal, do you have any questions related to conversion between vertical TEC to this flat TEC, or why we do that, and the disadvantages of using data that's already Madrigal? The main disadvantage, I would say, is you are not free to adjust the IPP or the Ionosphere Pierce point. So it's all the data that we download from Madrigal is already made available there, assuming that the ionosphere is present at an altitude of 350 kilometers. So if you have a really strong aurora happening at a lower altitude, then this assumption is not valid. Any questions, anyone? If you have any chat. So I hope you don't have any questions. Let's go into Madrigal. This data only for no. So Madrigal has data for all latitudes, so both the northern hemisphere and the southern hemisphere, for both high latitudes and low latitudes, not just for high latitudes. So I'll show you. I'll show how the data looks like, so it should be easy for you to follow. So if you're looking at GNSS receivers, Madrigal takes data from GNSS receivers across the globe. So no matter whether you are at high latitudes or low latitudes, or in the northern hemisphere or the southern hemisphere. If there's a receiver, and if the owner of the receiver has provided data to MIT, then that data is actually available for us to use. So except Russia, so Russian GNSS receiver data is not available. So you would, I'll show you those maps. So when you create those maps or look at the maps, you will actually see the gap in the Russian content. So otherwise, if you have data, we would be able to see all of those receivers and data from all of those receivers in Madrigal. I pasted the link in the chat for everyone to access. That's the main website where you can access the Madrigal data. So we're the screen. Can you all see my screen? The Madrigal screen. Anyone? Yes, good. So, yeah. So this is the Madrigal database at CEDAR. And you have some descriptions, you can read them. And if you are ever to use the database, always remember to cite this. And we'll write out his partner retired. Catherine Carolina, she's now in charge of the Madrigal database. So if you have any queries, you should be so you can either reach out to them or to the PI. Okay, so this is the main website. There's a tab on the top left. You can see access data, and then just click on mixed experiments. And that will take you to the Madrigal instrument web page. So here you can scroll down and see what all instruments Madrigal actually hosts. There are coherent scatter radars, like I said. There are the incoherent scatter radars. So let's say you click on incoherent scatter radar, and you can actually see what all instruments or what all data you have from the incoherent scatter radar network. You have data from Arecibo, you have from the IceCat. So there are different IceCat radars from Svalbard, from Tromsø, from Kiruna. So all of those data. And in brackets, you can see, for example, if you look at IceCat, Kiruna, VHF radar, you see the data available between 2014 to 2022. So the dates of the year in the brackets that tell you how long the data is actually available within the Madrigal database. So you have like all sorts of data from all different sorts of incoherent scatter radar network, images, ionosondes, magnetometers, even the geomagnetic indices. So you want to get the geophysical indices. So you can even get the A index, the magnetic field from the ACE and the other satellites. All of those data are also available at Madrigal if you don't want to use the or the NASA Army. All right. So what we are interested is in TEC. So you should be selecting the distributed ground-based satellite receivers. Right, so that's the second option from the top. Distributed ground-based satellite receivers. So that's for the GNSS receiver network. And when you select that, you get two options. You have the GNSS scintillation network, and you also get the worldwide GNSS receiver. So choose the second one. That's the GNSS receiver network from across the globe, where you would get the data for TECs. And you can see like the data actually dates back to 1998. So that's a very big wealth of data. If you want to do statistical studies spanning multiple solar cycles, then you can use the data from Madrigal to do statistics over, how much is that? 25 years or more. So your data from 1998 to 2026, so recent data. And then when you do that, on the right, you see a couple of options asking you to enter the dates for the start date and the end date. I would go for, I already have the 2024, the May 10th of 2024. So I'm pulling out only the data for the May 10th, 2024. Does anyone remember any speciality for that date? the 10th of May, 2024. Yeah, exactly. That was one of the strongest geomagnetic storm we had in this century. So the previous biggest storm of similar magnitude was in 2003, the Halloween storms of 2003. But then after that, we had the next severe storm of similar magnitude. I think like the CMH or the DST was below minus 200 or 3, minus 3. So that is a very intense storm. So that's why I just chose that storm for as an example. So just choose the dates, and then you can input the time. Usually I just put the entire day so that I can get the full TEC data for the entire day. But if you want to have like 1 week of data, you can have the end date after 1 week, so 17 of May. Or if you want to have 1 month of data, just give the next month as the end date. So it all depends on you, but it takes some time to load. But for simplicity, I'm just loading only one date, and then just list the experiments. That would actually take you to the next web page where you should be having the data. Yeah, can you see that? So it's automatically displaying the data for the 9th of May and the 10th of May, because since we started with 10th of May, the software or the algorithm that they use to detect the date inputted by a user will also pull out the date from the previous day, because the end is on the 10th of 00 of the 10th. So that date is for the 9th. The second one, that's the date or the data for the entire 10th of May. So that's starting from 00 of 10th until the early morning of 11. So that's the full day of 10 May. So that's what we are interested in. Let's choose that. Click on that. So that's the TEC data from GPS and GLONASS. So if you look at the title here, so all the receivers would be tracking GPS, Galileo, GLONASS, and other constellations. But what Madrigal does, they have started including Galileo, but it might take some time before we would have it in this. But at least right now, all the data that we will be using would be coming from GPS and the GLONASS, the Russian and the US solutions. Okay, so all GPS satellites and all GLONASS satellites that were visible above a particular receiver would be available on this website. And if you are going to use this data for any publications, then remember to contact Anthea, CPI of these instruments. Anthea Koster is the senior scientist and was the assistant director of the MIT Haystack. So you just contact her, tell her that you are going to use this data for publication, and ask if it's okay. And then select file. Over here, you would see different options. So the first one is the vertical tech data with the temporal resolution of 5 minutes. Right. The second one, that's the TEC data with a temporal resolution of 30 minutes. And then you have the list of sites that are actually used to make these maps or these data. So if you click that, you can actually see, or you can actually download. That's pretty fun. You can actually see like what stations actually contributed to this data set. Right, so you can see like the GPS site number. So those are the 4-letter codes that denote where the data is coming from. So if you want to see where these stations are, just plot this latitude and longitude on a geographical latitude longitude map, and you can actually plot it and see where these individual stations are located. But in fact, there are many receivers. So if you try to plot it, you will actually see the cover all around. So if you want to have a look at that, you can see that. But we won't be doing that. But what we are interested in is choosing the TEC data separated by or by 0.5 minute resolution, and bin file one by one increasing latitude and longitude. Right? You can download the file. Just download it as is. So that will just give you all the required parameters, including TEC, the errors associated with that. This is an HDF5 format. Just click the download button here. If you haven't downloaded it, just feel free to download it. It might take some time. You want to follow the session that we're going to look at later. Then you need to have this at least one of these files downloaded in your local computer. If you haven't done it yet. If you have it, that's good. You can just go ahead. So that's how you download it. If you want to have the line of sight or the TEC data with a higher temporal resolution, 30 seconds, then again, choose as is, download it. This will take, like I said, a lot more time to download because it's bigger file. So it's sampled every 30 seconds instead of 5 minutes. So the file that I had was approximately about 12.5 gigabytes. So that's huge. And we won't be able to load that big of a file into before crashing the kernel. So there's a good way to actually load it in chunks. So I'll show you how to do that before or without crashing the kernel, because it takes a lot of memory. All right. So that's how you download the data into your local computer. Then if you want to cite it, there's a format for citing it. Again, like I said, you can follow the format, but always remember to contact the PI of this instrument. Not just for GNSS, if you're using any other instrument for Madrigal database, like ASCAP radar data or geophysical data, there will be an associated PI for those data. So just feel free to reach out to them and tell that you're going to use it for some application. And finally, there is a view file info button there, and that actually tells you what this file actually contains. So there's a lot of information here. You don't have to worry about any one of them, but it actually tells you like who developed it and who helped compile all of this data. So you can see here, for example, the receiver biases that Ben was actually mentioning, that you can actually download from one of the IGS for yourself and correct it to get more accurate TEC values. If you want that, you can do it by yourself, but Madrigal has actually done it. Like Science Madrigal, sorry, at MIT has actually done it for us. They have corrected it, and the procedure, if anyone wants to see how the receiver biases have been corrected into the TEC calculations, just follow this link here for the paper. That's done by Juha Verenen. He's an assistant. He's a professor at the UIT in Norway. So if you want to really read and go in depth on how those biases will calculate, you can just have a look at it. So there are more information here, how the errors have been corrected, and what observatories have contributed to the data. You can actually find it here. So those are the observatories or the stations that have actually contributed to the data, which you also need to cite if you actually see it. And finally, if you go into this file that you have downloaded, these are the experiment parameters that the file will actually contain. Okay, so if you have experiment parameters and some data parameters, so it will actually tell you what individual columns are. So you will see like year, month, day, hour, minute, seconds, separate columns. If you are loading that pandas data frame, then you can actually have separately as columns. You have the GPS site information there, so you know exactly where the data is coming from or from which latitude the data is coming from. The PS altitude, like I said, it's usually they assume 350 kilometer. I think they have mentioned it somewhere here. If you read. You can go through. You can go through both the file descriptions, but also you can plot this the geologic latitudes and longitudes of the reference stations so that you know where the stations or where the data is coming from. What we would be using is the TEC, which is the vertically integrated TEC that's directly made available for us by correcting for all the biases, for the clock errors, the errors due to temperature. But again, there would be some errors associated with these TEC values. So if you're don't take the absolute values of the TEC for granted; those are not very accurate, but they are the best that we have. So I never have used the absolute TEC values for anything. I mean, I don't really need comparison between the TECs between different satellites, but what I have done is mostly looking at how the Ionosphere behaves in a global sense or in a very complex region. So I was more interested in seeing structures propagated across the field of view instead of comparing individual TEC values between the satellites. But you can also do that, but just remember that there is some sort of uncertainty associated with those regions, TEC values. Then we can also use the azimuth and the elevations of the satellites to calculate where the latitude and the longitude of the measuring point is. If you want to do that yourself, if you don't want, you can directly use the latitude and longitude values that's directly calculated by Retrieval. All right. So you can go through that. Then there is also satellite ID. So if you want to know like what satellite is contributing to the measure TEC. So for example, if it is GPS 2 or GPS 5 or is GNSS 20, that information is also provided along with it. So it's a complete data, very, very well arranged, very easy to navigate. But there has been like a big procedure that has been followed by the MIT base before making the data. Okay. So download file as is, download it into your local computer, and then we start analyzing. The good thing about downloading it is that we can tweak it as per our requirements. So if you want to only concentrate on low latitude, just equatorial belt, then you can adjust the latitudes in your Python or MATLAB if you're using MATLAB. Or if you want to concentrate at high latitudes, then you can just adjust the latitudes to concentrate at high latitudes. Or if you want to have like bigger resolutions, you can also do that. So that's a good thing about writing our own posting download file and processing. But if you want to have quick looks, like if you want to see if like there was a magnetic storm, a geomagnetic storm, you want to really see if there was something interesting happening at your preferred latitude or your preferred hemisphere, then these guys have also made available the blocks for this TEC. We're going to look at the 1 by 1 degree by 5 resolution. Those are much more smooth maps. So just click on plots or docs. You'll get a lot of different options. Just click for TEC maps for the day. And that will open up a new tab. Pick some line for you to show. Can you see it? Share this tab. Okay. So that's how it would look like. And there are individual images that you can actually see here. That's plotted every 20. So these are very, 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 very much smooth images of TEC. So where you have coverage, all the data that's available from the receivers have been used. Many parts of Russia, like I said, is empty, just about China, and that's because those data are not available to them. Many parts of Africa and some parts of India, actually many parts of India are also not available because we don't have proper receivers there, both in India and Africa. So that's one of the main reasons. So this is the data that you would see every 20 minutes. So whatever happens, the Ionosphere for that 20 minutes have an average. So high chances that you will be missing out local features during those 20 minutes. There is an animated GIF or movie formats that you can download. So on the top here, you want to play the TEC maps and just go through the entire day of TEC. You can actually do this animation yourself. And you can see how the TEC is actually evolving both in the northern and the southern hemisphere, and also at high latitudes and low latitudes. This thick region of density that you see around the geomagnetic equator, that's the, you remember from your lectures, that's the Victoria transition anomaly between your lectures. And this was the storm thing. That's where you see like big density structures propagating across the US from the low latitudes. Actually, it's propagated from low latitudes from the Latin America towards the higher latitudes across the US and into Canada and the Northern Hemisphere. So that's the storm. So that's a quick map, quick picture that you can actually see if you want to compare or have some idea on where interesting things are happening. Share again. So, there. All right. You can also go down to line of sight data. Let's go there. Again, the same plots. Can you see it? Can everyone see the slide that I'm showing right now? Good. All right. So if you again click on plots, you can again look for the maps here. So the second option, if you look for the second option for the raw line of sight data, so that's the data plotted every 5 minutes. Okay, so then you would actually see data at a resolution, much more high resolution that's obtained from the 30-second data. So they would average over about 30 seconds, and they would actually show you what the so it looks like global, which is much more precise, obviously, because we are not averaging over bigger time intervals. Okay, so that's how it will actually look like. So you can again have this as a reference and see for yourself like how the TEC data looks like as when you compare it to what you have. All right, so that's how you go to Madrigal, and that's how you provide data. Any questions, or anyone have any questions on how to download anything related to the data pulling from Madrigal? No? All right, let's go back to the lecture over here. So like I said, two types of data depending on your need. You can go for 5 minutes or 30 seconds. 5 minutes is much more. It's not too much of a load for your computer, but 30 seconds, that's a big file. Very and you can download the data from Madrigal. Again, the slides will be shared for you, so you know you will have the link for that. All right, so if you want to really do analysis for yourself, so for example, on a project that you might be doing soon, you might have, I don't know, like what you would be doing, but let's assume that you're doing, you're comparing a geomagnetic active day with a geomagnetic week, and compare what's happening in the ionosphere between the 2 days, so that we know how the ionospheric dynamics varies between an active and a quiet day. In those cases, it's always good to download data from Madrigal and analyze everything. So this is an example where I downloaded a 5-minute resolution data from Madrigal for 2 different days. On the left, you see data from 2013. That was a solar, that is during the previous solar maxima, 2013. And on the right, you see the plot from 2024, the same geomagnetic storm. You can clearly see that this is just concentrating in the high latitudes. So my code, I just adjusted the latitude range between 60 to 90. That's it. If you want to expand it down, you can go from 0 to 90, so you know how the entire northern hemisphere would actually look like, assuming you look down from the north pole. So this is the view that you would have if you look down from the north pole into the or onto the ionosphere. Right. So the different countries have been plotted, and the coastlines of the different countries have been plotted. So I was just concentrating for my study that I did on the northern high latitudes. I hope you all are aware of the magnetic latitude and the magnetic local time coordinates. So it's simply, if you are not, it's simply coordinates just like geomagnetic latitude. Sorry, the geographic latitude and longitude on the Earth. But instead, we would convert everything to magnetic coordinates, because we assume this coordinate system to be fixed and Earth to rotate around it. So the good thing is that you would actually know like where the structures are coming from and where they are actually propagating, instead of just focusing on a single geographical region. And so on the left, you can see a big dense red region. So this is a color plot with colors going from 0 to 30. Values going from 0 to 30 with associated colors. So higher values mean higher time. So 30 means, so I've just stopped at 30, but you can also go for 35 or 40 depending on color scale that you want. But what this says is that on the right, where we have the morning segment, that's where we have very low dense plasma. So the average TEC is less than 5 10. It's very less. But when you move to the noon sector, so that's where you have the sun mostly radiating into the ionosphere. So that's the noon sector, like early morning for people in Norway and in Greenland. So that's the most of the ionization coming from solar ionization, water ionization. And you see very dense plasma sitting at the lower latitudes, and you can see some structures propagating into higher latitudes. Does anyone know what that is? A structure that moves from lower latitude into the polar regions. If you had listened to the JS lecture on the ionospheres, you might have talked something about the high latitudes. Does anyone have any idea on what that is? Specific location. You can, like, for when you download it, you can download the data, and then when you download the data, you can adjust. So when you load it into Python, you can say, I just want only data between, let's say, 20 to 40 degree latitude and 50 to 80 degree longitudes. So when you specify it into your Python script, it will just pull out data from those particular regions that you can replot it there. So yes, you can do that. But if you want to download it particularly for a specific location, then I think you can do so. Just below the axis, you can have the select parameter. Perhaps you can adjust it there. But I would always advise to download the full file, and then when you read it, just read whatever you require, right? Yeah, so that's an E cross B drift across the high latitudes, yes. But the structure that I was showing, the little red structure that you are actually seeing, this red feature, that's what we call a tank of ionization. That's again enhanced density of plasma fluid extending from lower latitudes into higher latitudes. Okay, and on the right you can see such a really strong tank of ionization extending all the way from the morning side, which is, or the noon side, which is 12 MLD, to the night side, which is 0. So that's a big structure stretching all the way from the morning sector to the night sector. So that's huge. The data for yes. So like I showed you, along with each of these data file, you would have the station code. So if you know what station codes are for the receivers in Africa, then you can get those data. If you don't know the station code, like I said, associated with each station code, you can also have the latitude and the longitude of that station. So if you're, let's say, you're interested in the African region between, let's assume between 20 to 40, 20 to 30-degree longitude sector, then just look for data, or not by eye, but it's much more easier to do in Python. Just ask Python to select data between 20 and 30-degree longitude. So that will just give you data for the African region. And yes, you can do that. So I think like Africa is between, I don't know, what is the geographic latitude? Oh, sorry, the longitude for the African continent. I think it's roughly 20 to 40. So if you enter 20 to 40, when you read it, you can basically output, like get only the data for. Yes, I'll show you. I mean, we can do that. I'll show you how. Yeah. So that's how a 5-minute resolution map looks like. If you want to zoom in to a particular region, like one of these western states. So this is our zoom for Svalbard, which is in Norway. So that's a very zoomed in map. So I'm only looking at what's happening around Svalbard for 3 different time intervals. And you can see, instead of this extended feature that's uncut, you can see smaller features that are moving separate, and that's like these red structures that you see. That's what we call polar cap patches. And those are plasma structures that propagate across the high latitudes, predominantly formed from plasma fluids that are coming from mid latitudes or even low latitudes, propagating across the high latitudes and creating disturbances in GNSS signals. And that's why we study polar cap patches. Okay, it's for the same day, but I just zoomed in and I just showed you, like, we can also zoom into a particular region to see features that might otherwise be in this in a bigger dot. Right? Now, to answer your question, yes, I'll actually show, yes, of these plots. Yes, we do have the, I do have the Jupyter notebook files in the same GitHub folder where Ben had all these before the files. So we'll run through them now. Like I said, so like Osman, so you're asking for if you want to just get data for Africa. So this is not Africa, but this is just for the US. So I just focused on the geographical regions covering the continental US. So this map is in geographical coordinates. The previous one was magnetic coordinates, like geomagnetic latitudes and geomagnetic longitudes. So you just need to know both, because both would be handful, or like would be very handy for you, depending on what science case you are interested in. So I just have made like both of them available for you to use. So if you are interested in only a particular sector, like Asia or Africa or the US, just select the latitude and the longitude region that you're interested in, and then plot these maps. And this map is created at 30-second resolution. It's much more precise, and you can actually see smaller features. So you can see something around the ocean coming into the field of view. Can you see that? Like, you can see my cursor, like a red region around the ocean towards the west side, sorry, the east side of the US. That still remains for approximately 3 hours. But the interesting thing is that that's at night time. So when US was having nighttime, local nighttime, we don't expect such big enhancements in tech. And this was something I investigated when I was at MIT. We don't know the cause of that, but we know that when we have such features, we were experiencing severe disturbances of GNSS. So that was a good study that we did. But such studies or such TEC maps that we create. So these maps are created using data from receivers all around the US. This is not data from just a single receiver. These are data from all the different receivers from around the US. So if you want to do just what Ben did, you just have to like download all the data from the receivers, do the phase leveling, bias estimation, corrections, estimation for the other satellite drop errors, etc. You can do that obviously, and you would end up with a similar feature. But the advantage that we can have by using Madrigal data is that you can get the data which has been corrected for all of these errors and biases directly. That's good. You just have to like plot it and adjust the geographical region that you are interested in. All right. So let's make some TEC maps. So like I mentioned earlier, people who have downloaded the data, I mean, we need to have those data, like two sets of data, the 5-minute resolution and the 30-second resolution data. Make sure to have them downloaded. If you don't have it, please download it. Depending on your Wi-Fi speed or the internet speed, it might take a lot of time. So, Amadi, if you had sent the instruction slide that I shared with you earlier yesterday, many of you might have got the data already downloaded. So if that's the case, then you can follow the Jupyter session with me right now. Otherwise, it's simply straightforward. You just have to like run Jupyter notebook. So if you go to the GitHub folder, the same one which I've been shared with you, there's a iFile notebook file called Reading Madrigal TEC. Just have to download it. Reading, stop share. Right. So reading. Okay. There you go. Can you all see my notebook? The Jupyter notebook that I have shared now. So just go to the GitHub folder and download the reading Madrigal TEC.i file. That's the exact file which I have. Can you all see the notebook which I have, which I'm now sharing instead of the presentation slide? Okay, great. You can load it. So I'm using Jupyter Notebook. It's not more convenient for me, but it's the same file. So you can also load it in VS Code, which will fine. We would be using some other Python libraries. In case you don't have it, you would have to install. So I've listed like the data site where you can download it, the Madrigal data site. And also, in case you're missing any of these libraries, just open up a terminal and do pip install. Pip install the required library that you're missing. So if let's say you're missing the AACGR library, then just do pip install AACGR in the virtual environment where you're running current Jupyter notebook. Here. So when you first run it, you might not have some of these libraries. I'm not sure, but if you have used it, you might have all the libraries. So you don't have to worry about that. In case you're not having it, just do pip install. I think if you're using VS Code or even Jupyter Notebook, you can even install it from a terminal. You can even install it within this notebook set. So let's say ASCGM V2. You can just do, yeah, you can just even install it within the cells of Jupyter Notebook or even VS Code. So in case you don't know how to do it in the virtual code, the virtual environment, you can just install it within the Jupyter Notebook cell or the VS Code cell that you are currently running. The only thing is that the next time you open Jupyter Notebook, you will have to reinstall all this, right? So the good thing to do always is to have it installed your virtual environment, so you don't have to reinstall it every time you open up your Jupyter Notebook. Right. So you can start running it. So like, so I already have this library installed, so I'm not installing it again. So the second cell, this is where you would give the data path. Okay, so that's the only thing that you have to do it yourself. So there's this main folder. So I have highlighted it using the change data file path here. So remember to put the path of the data. So if you have downloaded the data to your document section, just put the path of your document section. Or if you have downloaded to your download section, just give the path where the data is. So change the path here. Change the path to the data here. Then if you enter, you're asked to enter a 8 in this format, 10 underscore 05 underscore 2024. So that's 8 DD YY format. So we downloaded data for the 10th of May 2024. Just input it, and that should automatically take it in. Right? Then let's start analyzing the 5-minute resolution data. So create the data frame. So everything else you don't have to do anything. If you provide the path to the data correctly, then all of these cells will execute automatically. You don't have to worry about that. So this script is in the same GitHub folder which Ben shared with you earlier. So here, so everything is here. So everything what Ben had and everything what I have, everything is posted on the same repo. So you can just download it from the same GitHub repo. So if you go there, you can see a file called reading Madrigal tech. So that's where you get download. All right. So I usually love working pandas data frame. So that's why. Yeah. So that's why when you have it loaded, when you have the correct path, you would see the data printed as a data frame. So all the required columns with the titles are given: year, month, day, date, latitude, longitude, TEC. Everything is arranged very perfectly with the columns, so it's much more easier for me to work with. So that's why I usually like working with the pandas data frame. All right, so that's how. And then here, I'm only choosing data above 50-degree latitude. So this is where if anyone wants to change the latitudes from 50, let's say you want to go from 0 to 30, just change it here. Okay. If you want to go from data from 20-degree and above, just change 50 to 20. Okay. So that will just give you data everything above 20. So that's the query. Like dot query in Python means we are telling Python to choose data based on what we are giving inside. Okay. If you want to have data between 20 and 50-degree latitude, just use GD latitude greater than or equal to 50, and just use the symbol and GD latitude less than or equal to 50. Okay. If anyone wants to use data, let's say someone asked me that GD long, I think it's G long. Yeah. So if anyone wants to use data for the African sector, let's say Africa is between 20 to 50 or 20 to 50-degree geographic longitude. So I'm gonna use this query instead. Glon less than or equal to 50. So this would just pull out data between 20 and 50-degree longitude sector. So that's the African sector if you want. And you can adjust it. So that's where you have to tweak the data. All right. That's how you tweak. All right. Then I simply add a data type column for the exit. Okay. Just ran it before. Here output. There we go. I just ran those sets before, so that's why it's saying that the column exists already. All right. So now we have the data column inserted. Then I'm inserting a column for magnetic latitude and longitude. I'm using the AACGM coordinates. That's the altitude adjusted corrected geomagnetic coordinate system. So we use that to convert from geographical coordinates to magnetic coordinates. And then once the conversion is done, takes some time. I mean, less than a minute usually. It will actually give you the magnetic latitude, longitude locations, and put it as a column into the data frame. So we have a data frame now, even magnetic properties inside. Let's now finish running it. There you go. It's completed. And then let's pull out the data we really need to do for plotting. So I'm plotting TEC in MLAT and MLT for the magnetic latitude and right. Then there are some functions to convert from magnetic latitude to geographic latitude to magnetic latitudes and longitudes. And this is the big script which I have written to create these global TEC maps. Okay. What I do here, if you are interested just to plot as like a scatter plot, you can just use the scatter plot on your own. But I'm particularly using the p-color mesh feature of Python, so that it will interpolate with data at the like regions where there is sparse data. So you would have a much more smoother coverage. You can see like regions much more clearly. So I'm just using a grid of p-color mesh. And this here, this first line here, sorry, the 10th line here, for TT in TQDM range 1991. That's where you can change the number. I've left a comment there. Change here to change the associated date time of the TEC map. So let's say you want to create the TEC map for morning 10 o'clock, 10 a.m. UTC. Then you have to change the number there. 90 to 91. Let's say you go to number 20 to 21. So that will create the TEC map for the 20th. So, okay. If you want to get the map at the evening UTC, then go for something like 140. If you want to create maps continuously or for the full day at a resolution of every 5 minutes, then you can adjust instead of 90 to 91, you can go from 0 to the last number. Whatever the last number is. If the last number is 300, then go from 0 to 300. So it will just keep on plotting iteratively, continuously, and just give a save figure function at the last, so that it will just automatically save all the plots into your preferred folder. So that's much more easier. You don't have to like every time keep on changing the numbers. You can get all the figures saved to your directory directly. But for the current time, let's stick with 90 to 91, which is one of the date times, and let it run. It should create a TEC map for, yes, there you go. You see that? Yeah, it's creating a TEC map for the 10th of May 2024, and the time is 7:30 to 30. That's UT, 7:30 UT. Right? I'll show you how to change it. Let's change it from 90 to 91. Let's go to I would say 180 to 181. Let's run it again. You should be seeing a TEC map for a later time. So previously it was at 7 UT. Okay, this is at 15 UT. Okay, so this has actually changed. the TC map has changed. And see the gap here? That's the gap I was mentioning earlier. It's the Russian region where we don't have it, population. So you will always see a gap, the Russian side. And this plot, like the coordinates here, they stay fixed, but the countries, they rotate. So Greenland, look at Greenland here. Greenland is close to 12 MLT. If I choose an earlier time, let's go back to 1991. That should be early. So Greenland would actually rotate, or in fact, the entire Earth is actually rotating in a fixed MLT, MLAT coordinate system. There, Greenland is now somewhere around 6 MLT. Okay, so these countries will rotate. The labels, they stay fixed because magnetic coordinates, they don't change. So that's the advantage. So we can actually see that how structures are moving across the sky, without having to worry about which country is on the sky. All right. So this is how you make a 5-minute resolution TC map. In case anyone wants to change the color map, so I'm using a color map called Turbo. So if you want to change the color map, there is an option to change it from choose map instead of Turbo. You can, let's say, you go to Plasma. So choosing Plasma instead of Turbo. So just choose it. I mean, it depends on everyone. So if you are interested in getting a color map, in Plasma, which is I think good for presentations because it's equally it has got this like linear color scheme, which is good for people with the color blind as well. So in those cases, it's much more convenient for people. And if you want to change it, you can always obviously go to this option here for color map and choose Turbo or weight-based or Plasma, depending on which one you're interested in. That's how we do it. All right. I hope those are clear. The only thing that you have to worry about is giving directly the path to the data. Okay, just make sure that the data path is given correctly. Then this will work just fine. And then if you want to adjust or tweak the latitude regions or the longitude regions, just change it there. And the times, like I showed you, if you want to change the times required, if you want to look at the evening sector or the morning sector, you can adjust the times accordingly. Okay. Any questions before I show you how to do the 30 seconds? Right. Well, see any questions? Let's move on to the 30-second resolution data. Like I said, 30-second resolution is much more memory consuming. So again, let's stop running it. You'll begin ask for a date. Just enter a date. I've chosen the July 20, 2023. That's it. Make sure, so you don't have to change the data directly or the data path here. Just make sure to put the 30-second and the 5-minute resolution data the same path. So you don't have to go back and change the paths and the differences. Can we see from the equator side? Do you mean instead of having, or you mean including the equator from 0 to 90 degrees? Is that what you mean? I mean, if you want to see all the way from 90 degrees to equator, like I said, so first thing you have to include geographic latitudes going from instead of 50, you have to go all the way from 0. So that any data that runs from 0 to or above 0 would be taken, would be loaded in the database. If you want to go to the equator, so here on line 62, here I'm choosing the limits. So just fix the limits from 90 to 60. If you want to go to the equator, let's say you want to go until 0 degrees. Always also remember, when you change the limits, also change the labels from 60. So include 60, 50, 40, 30, 20, 0. Otherwise, you won't see the limits. So you can obviously do that. You will, if you have the data loaded from all the way from 0 degrees, you will actually see plots all the way from equator to the high latitudes. So that's how it would look like here. 60 ends here, but I haven't loaded data below 60 degrees, so that's why we don't see any data below. If you had loaded it, then you would actually see data all the way up to the equator. But again, like I mentioned, you only see labels up to 60. That's because I haven't included. Where is that? I haven't included the labels, like the tick labels. Just make sure you include the labels from 60 to cover also up to 0. So 60, 50, 40, 30, 20, include those labels. So you will also see lines drawn as well. Right? So that's where you change the limits if you want to go up to the field. All right. Now this is a function. Okay, time data. This is a function that will take some time when you run it. This is the function that will take the 30-second data in, and it will make sure not to kill your kernel, because the data, like I said, is very huge, more than 15 or 12 gigabytes. You won't be able to load such big data into your memory at a time, so you would have to load it in chunks or pieces. So this function does that. And when you do that, read the first timestamp data. So we need to first run this one. This is gonna take, I assume, like about 2 or 3 minutes before you see something. So you'll have to run that cell for more than, or you just have to wait for that cell to get executed, right? So let's say you'll wait for that. So the purpose of running this cell is that we are going to load or try to tell Python that I'm going to load data in chunks such that only the first the timestamp will take this much amount of time. So the first timestamp that we're loading will take, I don't know, like what, 150 seconds or so. But the next timestamps when you load, that won't take this much of a time. So after that, now Python knows that it should be loading everything in chunks. Then after that, when Python is trying to read data for, let's say, 5 or 6 timestamps simultaneously, it will automatically do it within 5 seconds. So the first timestamp will take the maximum time. After that, everything would be just faster. Still executing. You can see here it's not completed. It will usually print the number of seconds it actually took for execute or for complete or read the first timestamp. Okay. We'll wait for some time. But if does anyone have any questions on anything that we have done so far? I hope it should be very, very easy, straightforward. From the equatorial perspective, yes, you can do it from the equatorial perspective, but then you would have to change it from the polar view. So if I just go back, so you see here projection MLT north. You have to change from MLT north. I forgot like what we are using. It says some like it should be like equatorial. There should be some option for equatorial projection. So the projection that I'm right now using is MLT north, which means we look into the ionosphere from the north. You can also have like you asked for equatorial projection. So you can just change. It's a Python feature, I think. Just look for all the projection. Like what is the wording that you have to substitute for instead of the MLT projected value. But usually when you go towards equator, less people work with magnetic latitude and longitudes, because towards equator, like low latitudes and mid latitudes, the ionosphere is mostly viewed from the geographic component. The magnetic latitude and the longitudes, mostly the high latitude people usually work, because they are mostly interested in looking at like how structures from lower latitudes move into higher latitudes. For example, like rectangle ionization or polar cap patterns. So these are structures that propagate from suborbital or mid latitudes, and they move into the high latitudes from the plasma convection pattern. So if we are interested in doing that, so the high latitude people usually use equatorial and mid latitude people have seen mostly working only with photographic. Okay. But again, like I'll actually show you how, if you want to have an equatorial perspective from a geographical point of view, you can do. Yes, EIA's equatorial ionization anomalies are best viewed from an equatorial perspective, or best viewed from the geographical coordinate system instead of magnetic latitude and longitude. So if you want to look at the equatorial ionization anomaly, I would recommend viewing it from a geographical latitude, geographical longitude coordinate system, as I will show you right now. Instead of magnetic latitude and magnetic longitude, because those structures doesn't propagate even to mid latitudes. They're within plus or minus 20 degrees of the geomagnetic width. All right, so the first time we ran that big file, it took about 187, so approximately 3 minutes to compile the measurements for the first time. But when you do it next time, or that's what I'm going to do next, so I have some 6 different times that I'm going to plot in a geographical coordinate system. So right now I'm not using, so the code is again a bit big. We are not using we are using scatter, but we are not using color P measurement, because since this data is huge, more than gigabytes, because it's a 30-second resolution, we have like a lot of data points. It takes very, very, very long period of time to actually read the data. So instead, we stick with scatter plots, and that's much more accurate than the grid, because since we have like lot more resolutions, the scatter plots are much more smoother. So it will give you the same impression as a grid that we got measured. So just run it. Again, there are options within the code to change the color maps. I'm just using Turbo. And the plot that you would be seeing right now would be the geographical coordinates. And this is the best way to picture equatorial ionization anomaly features. So I think I'm concentrating just the US part here. Let's wait for the figure. Yes, there. That says the US for 6 different time intervals for July 2023. So I've adjusted the latitude and the longitude. That's why you only see the US feature. If you want to look at features like plasma bubbles or equatorial ionization anomaly that stretches a lot more bigger longitude region, you can adjust it. So what you just need to instead do here is this region here. So change lat long data values that you want to focus on. So instead of, let's say, you want to go from, instead of 60 to minus 140, you want to concentrate on the Asian, African sector. So adjust the values accordingly. So you would want the so your picture would be for the Asian African sector. But if you want to have a full view of the global map, just like what we saw in the Madrigal database, then you would have to go from minus 180 to plus 1. So that will just give you the big picture of the full globe. It should take some time, but still would be able to see the full picture. Okay, so this is where you should adjust the values. All right. Did I miss anything? Yeah, so even just like before, there is an option to change the color map here from Turbo. If you want to use Jet or Plasma or anything like that, just change it there. Also, if you want to adjust the, so when you go down to like lower latitude, sometimes during geomagnetic storms, you have TEC values up to 110. So in those cases, you might want to adjust the minimum and the maximum end. So right now I have maxed it at 40 tech units. If you want to increase it, you just have to go back here, change the V max from 40 to 100 or 90 or 80, depending on what you think would be the best with the maps. All right. Any questions? That's how you do it with 30 resolution maps. Do you have any questions? Again, remember to put the data in the same path as the environment resolution. So those are not changing the data. So if you're comfortable with Python and change the paths in between, just feel free to put it anywhere you want. So that's the only thing that you will have to worry about. Otherwise, it won't. And also provide all the libraries for install. All right, we're running out of time. If no questions, I will just do the final part of the radio simulation. Can you all see the screen? So I'm showing you the screen right now on radio simulation. Yeah. So simulation, some of you might have heard from the previous lectures. But this simulation, that's simply, I would say, something's very similar to twinkling stars. But twinkling of stars happen in the visible region. So again, when I'm sharing the screen, since I'm on Ubuntu, I don't really see your chat and your messages. If you have any questions or want to stop me, just feel free to unmute yourself and just shout out, right? Okay, so it's something very similar to twinkling of stars, but it's happening in the radio frequency. That's it. Okay, so you won't be able to see it with your eyes, but the receiver, a radio receiver that's capable of seeing recording radio signals, will be able to see this twinkling, and they would actually look like these rapid fluctuations. So instead of having a smooth signal, you will have rapid bumps with bigger bumps. That's how a simulation signal will actually look. Now, whenever we analyze signals from a GNSS satellite, we usually measure the amplitude and phase, or the signal strength phase. Right? And whenever we have variations in the electron density in the ionosphere, this amplitude and phase of the signal is perturbed. So the ionosphere, when it's perturbed during geometric active days, would have structures like polar cap patches, equatorial ionization anomalies, or plasma bubbles. This can significantly affect the amplitude phase of the radio signals. And that's what we call scintillation, okay? Rapid variations in this amplitude of the phase of radio signals. Interestingly, this was first observed by astronomers, astrophysicists on radio, on the space physicists. And these were observed during one of the observations of a radio star in the Cygnus constellation. And it is, like, the history is very interesting because when they first observed it, they thought that the source of these fluctuations was very much inherent to the star in the Cygnus constellation itself. That was the first assumption. But when people measured it at two different locations, they were not able to see this rapid fluctuations. So if it was inherent to the source itself in the Cygnus constellation, then no matter where you measure it from Earth, should be see similar fluctuations. But since people separated by about, I think, like 100 kilometers, were unable to measure similar fluctuations, they concluded that it should be coming from somewhere else. And that's how this relation, the theory got up, or how we started our analysis on simulation, or the interest on simulation. Now, this is important for mainly two purposes. One, to study the physics of the ionospheric irregularities of the ionosphere. So when we have simulation or radio signals going through the ionosphere, if there is a perturbation, it's telling us there are some density structures, or there is some sort of clumps in the ionosphere. You can study the physics of the ionosphere. You can understand the dynamics of it. Okay? It's also important for the society because when you have scintillation or rapid fluctuations, the receiver will not be able to capture the signal from the satellite very precisely. So it might lose stops on the satellites, and that can affect positioning and navigation. And that will affect a lot of industries, starting from agriculture to civil aviation, even hospitals that depend on radio signals from GNSS systems. I think like during the May storm in 2024, farmers in the US had to stop farming, I think, for more than 2 hours before GPS was available, because the positioning accuracy was more than some meters. The receivers were unable to track correctly the signals or calculate the position of the receivers themselves just by tracking the GNSS because of the rapid scintillation that was occurring in evolving as with geomagnetic storm of May 2024. So that's very important in terms of both scientific aspect and also for society. So here is an illustration showing you how scintillation actually works. Sort of like a simple schematic. So as you have a plane wavefront coming from a satellite, that's in ionosphere, that's in blue, with some irregularities, by some reddish chunks. When such a wavefront is incident on the ionosphere, what you have is like interference happening between wavefronts that meet irregularities and wavefronts that do not. Right? So according to Huygens principle, each point on the wavefront would be acting as a source of new wavefronts. Right? So because of these irregularities, the part of the wavefront that's meeting the irregularities would have a slightly different phase than the part of the wavefront that doesn't meet the irregularities. Okay? As a result of that phase shifted wavefront as it exits the ionosphere, they will undergo constructive and destructive interference, forming interference pattern on the ground. And that's what we see as scintillation. Right? So we use GNSS satellites that transmit in the gigahertz frequency to track scintillation and study the ionosphere. Particularly, we'll be using 50 hertz or data from receivers that operate at 50. So that means every second, we have 50 data samples. So every minute, we will get approximately 3,000 samples of signal amplitude and signal phase. Okay? And if you take the Fourier transform and make a power spectral density of the received amplitude and phase, this is how they do. So it's a power law. It would have like a power law behavior. So the red is phase, amplitude, and the green is phase. The difference between amplitude and phase is that amplitude usually has a flat slope until a cutoff frequency called the Fresnel frequency. And that frequency is important because that's the frequency that separates refractive and diffractive contributions to scintillations. Or in other words, you could have a big plasma moving across it in the system, and if it is moving fast, it's simply a change in the plasma density before and after the structure move, right? So it's simply a change in the refractive index of the ionosphere. But if there are small irregularities, then you could have this interference happening, constructive and destructive interference happening within the wave, and that's diffraction. So those are two different aspects. So diffraction is primarily captured by the amplitude of the signal. So that's why you have a zero slope until a particular point, and then a roll off. But phase usually has a single roll off without any cutoff. Okay, so that means the phase is dominated by both refractive and diffractive variations, but the amplitude is primarily due to refractive variations of the plasma density structures. Now, V sub C, the first cutoff, that's the cutoff that we use in our algorithms or by any GNSS receivers. So usually the manufacturers of the receivers have a cutoff of 0.1 because they want to remove low frequency effects such as due to satellite motion. So as the satellite is moving slowly, that motion will also be captured in the receiver phase, the signal phase. We don't want that. We are only interested in the ionospheric contribution. So we remove or we filter or those lower frequency contributions which are not ionospheric using a cutoff of 0.1. So that's this V subset. Right? Does anyone have any question? Let me go back to the chat. No. Is there any difference between this data set and GNSS data set integral? What do you mean by that? You mean, are you asking about the scintillation data or the DEC data? Yeah, I mean, is that about the scintillation or is it about the DEC, Madrigal DEC? DEC. So the data set that I showed you, that's from Madrigal. That's the same data set that's downloaded from all the receivers across the globe. So it should be the same. It's the same data set coming from the same receivers. There is no difference. So either you download it from the individual GNSS receivers from the globe, because it's the same receivers that are contributing the data to Madrigal. Madrigal, you can assume Madrigal to be like a big database where they store data from all the different receivers. All right, so that's how a schematic illustration looks like, but it's not really as smooth as that. In real practice, this is how it looks like. Right? It's the same different kind of frequencies, but this is how the red. Look at the red and the green part. So that's a bit noisy. The real data from the receivers look a bit noisy. So that's how a real data set that look like. Right? GNSS spectrum. Now, what we are mostly interested in is not the spectra, but the simulation indices, because you need to have some, just like geophysical indices like DST and CMEG. We have made simulation indices that can capture the effects of the irregularities on the ionosphere or on the GNSS. So we have two indices, S4 and sigma 5. S4 is simply the standard deviation of the captured amplitude of the signal intensity normalized to the mean intensity, and the sigma 5, that's the standard deviation of the signal. Okay, and S4, which is due to signal amplitude, that's sensitive to 300 meter scale irregularities. So if you have enhanced S4, that means there are 300 meter scale irregularities in the ionosphere. Okay, and when you have like enhancement in sigma 5, we say there are irregularities from scales from 300 meters to several kilometers, right? And the brackets here, that's an NSF average. So that simply means you take measurements over a given amount of time, let's say like 1 minute or 60 seconds, and you average it over 1. So you get values every 1 minute. But that's flexible. If you want to average data like every 1 second, then the brackets denote averaging over 1 second. If you want to do it over 5 minutes, then take all data for 5 minutes and average it over 5 minutes. Okay. So every GNSS receiver, yes, every scientific geographic receiver is capable of measuring scintillation, but not the receiver that our smartphones have. So our smartphones are those are very low cost receivers that can only track the signal phase, and then that signal phase is used to estimate position. That's how your Google Maps or Apple Maps work. They don't measure scintillation, but scientific geographic receivers that are installed by scientific parties, they can measure scintillation. And it's better to have like at least 50 hertz receiver, because scintillation, those are high frequency fluctuations. 50 hertz or 100 hertz, those are really good receivers that can measure scintillation very accurate. All right, so that's how we measure scintillation, and that's how the scintillation indices are calculated. What we will be using is the scintillation indices, right? That's readily available for us to use from different data sources. I'll show you one data source, but If you can basically get it from different data sources. But usually this is how a receiver calculates simulation indices. It collects raw power and phase. Those are the dot dots. That's how raw phase and raw power looks like, right? Raw phase is much more dominated by low frequency of the satellite version. So that's why you just see as a sync on. What we next need to do is a procedure called retrending, or in other words, we have to remove the trend in the data. So the trend in your phase is then on. So you have to remove. So we have to write. The receiver usually does it everything by itself. But if you want to do it just like Ben showed you, like if you want to calculate TEC by yourself, we need to do those the normal practices. So similarly, we have like standard procedure to calculate scintillation indices from the raw TEC, the raw phase and amplitude values. So in those cases, what we do is we use Butterworth filter and we use certain cutoff, usually 0.1 hertz, and we detrend it or remove the trend. And when we remove the trend, you would actually see those features, ionospheric features hidden within the signal phase mostly. But the amplitude is mostly very, very similar. We can but still remove this slowly varying phase, slowly varying the trends in the amplitude as well. So that would just leave you those rapid high fluctuations that are due to ionosphere. Those are labeled in those red marks. That's what we call simulation. All right. And then from those raw data in the second panel, we calculate simulation indices using these equations. So here I stands for signal strength or signal intensity, which is the second panel here. So you take signal intensity, which is recorded at 50 hertz, and then put those values here, take standard deviation, take the mean, take the square root, and you calculate the simulation indices. And that's how you get defined for this whole signal. Most receivers will output these simulation indices directly. So you just don't have to worry about calculating everything from scratch. But if you want to, but most of the receivers will output them only at a resolution of 1 minute. But if your science case studies, you use your simulation indices in 1 second, then you have to redo the calculations by yourself. You won't do that, but that's much more involved. What we would instead do is we would try to plot these simulation indices as directly output by a receiver. Okay, so many theoretically standard receivers will have simulation indices output directly, so we can just plot them and directly plot. So that's what we're going to do next. I can really quickly do that. So again, you can go to this website. This slide will be shared with you. So you can go to the website and download some simulation TEC data from a GPS constellation for 10th of May. And then again, go to the GitHub repository, download the second Python file called reading simulation data file. And then you can open it up and you can do all sorts of these exercises and play around with that. So what I'm going to do next is real quick show you how to run that file. Reading all right, there, reading simulation. Can you all see that screen? I'll make it real quick. We are almost out of time. So I'm showing you again. I've given the link to download the data. Again, this doesn't require as much libraries as the previous Madrigal database. I think you just have to have this AACGM and the TC installed. But again, it's very similar. The format is very, very similar. There are different stations. If you want to change the stations, you can do that. Again, remember to give the folder name correctly. Where you have downloaded the data, just give that data path correctly. That's it. The rest of the script will just take care of it automatically. Again, you'll be asked for a date. So just input the date for which you downloaded the data. So there are some functions to read the simulation data and to find the maximum S4 and sigma 5. And that's because at a given time, a satellite would transmit signals at multiple frequencies, L1, L2, L5. So what I did is like, I just wanted to know if there was simulation in any of the frequencies. So either you can do the minimum or the maximum or even the mean of that data during the time interval. I just took the max of all the given values at the given time interval from a given frequency, from a given PRF or a satellite. And then there is also a function to read TEC data from the same receiver simultaneously, and then find the maximum TEC value. And then here I would, so those are the functions. You can obviously, when you have time, go through it by yourself. I have used an elevation cutoff for all of these data. So I'm using an elevation cutoff of 40 degrees to remove multipath. If you want to decrease it, you can decrease it. If you want to increase it to 50, you can change those values there. And that's both for both scintillation and also TEC. Right? So there are two places where you can change the elevation cutoff. And then make the scintillation and the TEC data frames. I usually work with data frames, so let's make everything as a data frame. So that's how a data frame would look like. You would have the station you're working with, what constellation, it's GPS, what satellite you're looking at, signal type and everything, the GNSS, the elevation values, the sigma phi, the S4 value. Then some functions to remove and correct for S4. Because S4 is sensitive to noise, so we remove the noise term to just leave the ionospheric part. That's some adding latitude and longitude for the data frame, and again magnetic latitude and longitude if you want to overplot it on top of the Madrigal TEC files. Loading the variables, and then finally just plotting. It's much more simpler, much more quicker, and this is how the simulation of S4 and sigma 5. The top two panels are S4 and sigma 5. That's how it would look like. And the last two panels are VTEC and rate of TEC. Rate of TEC is simply how fast TEC is varying. It's simply telling you about the presence of gradients in the TEC structure. So interestingly, you can see like increase in S4. So the black horizontal line, that's its threshold 0.1 that we use to separate scintillation versus no scintillation. We mostly assume everything less than 0.1 is no scintillation. There is no disturbance, and everything above 0.1 is scintillation or disturbances in GNSS. So that's why I have that horizontal bar there. So clear increase in scintillation after 20 UT in both S4 and sigma 5, and that's associated with a big TEC jump. It's clearly see how the TEC is jumping with a great dip. So that's a TEC structure. We don't know what structure that is, but you can make a TEC map and see if that's a type of ionization, or is that a plasma bubble, or is that a patch. But what we can know from here, because this is a single station, not many stations like the Madrigal database, you can see that the TEC has a big, deep gradient. So that means there is a big chance of having plasma instabilities, like relative instability or Calabi-Raman or gradient drift instabilities that can create different damages and create different scale structures. And that's exactly why you see these pieces spoke about exactly at the same location and time as this increase in time. Okay, that's why increase in TEC plus increase in scintillation. So that means there is something very interesting happening during that day. I have some exercises for you. You can try out yourself, but play with different constellations. So this is just GPS. You can download for Galileo or Jonas, or even for different stations. Like there are other stations that are available in the database, so you can download it and see the spatial distribution of variations in simulation. And do a lot of physics there. You can opt scintillation from raw GNSS RINEX. So if you're working with RINEX observation files, remember RINEX files will only contain data at least every 15 or 30 seconds. They don't record it every once. So if you want a steady scintillation, I would not recommend using RINEX files, because scintillations are recorded every 50 hertz, which means that you would have values every 0.02 seconds. But most of the RINEX files uh, would have uh, data available only every 15 or 30 seconds. So you would be missing the scintillation aspect if you are using such RINEX files. Yeah. So I would highly recommend using just the raw file. So if you want to use scintillation, just reach out to the receiver PI and ask for raw power and raw phase measurements. And you can calculate it from that instead of RINEX. RINEX usually doesn't have 0.0 second resolution. People never do that because it's huge. Yes, we are almost done. But if you have any questions, you can always reach out to me. Yes, Amadi, yes, we are past time. Yes, but if anyone has any questions before we wind up, I'll take some more questions.
Yeah, sorry, my network did not allow me to introduce you at the beginning,
Okay,
and
no
I
worries.
was thinking, yeah, I was thinking that maybe towards the end, towards the end, I will be able to introduce you. Unfortunately, you're so passionate about teaching everything, so you
Yeah.
had to encroach into your time again. So on my side, I want to appreciate you. I think every question can be sent to you or asked in the group, and it will be passed to you. For those of you who are still here, it's important to know that Mahit is a great researcher, a space physics researcher at the Arctic University of Norway in Norway, and currently a visiting research fellow at Boston University in the United States. And he obtained his master's from the University of New Brunswick in Canada. And in fact, he has two masters and just concluded his PhD, and an expert in GPS data analysis and so on. And he's
Mhm.
also passionate about teaching, research, science education, and so many aspects of science communication. So thank you, Mahit, for your passion, for the knowledge you've inculcated today. It's highly appreciated, I must tell you. You gave more than we asked for. So we asked for so small, so little, and you give so much more. In fact, more than what was contained in the curriculum. We just said you'll be shown how to fetch the data and then plot it, and that's all. But you went deeper and deeper and deeper and kept digging and never wanted to stop. So thank you very much
Yeah.
for the
Thanks, Amadi. Yeah.
for
I've
the
also shared my
insightful
email.
teaching and knowledge.
Yeah, so I've also shared my email if anyone wants to reach out. So all the Python scripts, the Jupyter notebooks, so I have written them myself. So if anyone have any questions, so you can always reach out to me if there is anything like they find it difficult. So yeah, I would be very much happy to help.
All right, thank you very much once again. We have a group, and I will relay any question they have. And since you have shared your email, they will also be able to reach you. Thank you for that. And this recording will be made available on YouTube, so they can watch over and over again. Maybe if there are areas of misunderstanding, they can straighten it out after watching maybe once or twice from the recording. So thank you very much for your time. It's appreciated, and I believe the participants really appreciated uh, the presentation. Thank you. So In the absence of any question, I think we can call it a day right now. Okay,
All right.
Mahit.
Thank you all.
All right, have a
Thank you,
great
Emilio.
weekend.
Yeah.
Okay,
Thank you
bye.
all. Have a good weekend, everyone. Bye bye.